Howdy. The point of this video is to discuss how to index points in crystallographic space. Now, why do we want to do this? The main reason is that we'd like to describe the location of atoms or vacancies or some other point feature in a crystal lattice. Let's look at an example. What we have here is the structure of quartz, which is SiO2. So we see some silicon atoms and we see some oxygen atoms. Now, any crystal lattice is made up of two things. We need the principal lattice vectors. We have A, B, and C. And these each have some magnitude, some length, and some orientation relationship relative to each other. But in addition to that, we need to know the position of the atoms within that lattice. So for example, how do I describe the position of this particular silicon atom? And I do that by defining a vector, let's call that R, and describing the length of R in terms of fractional coordinates of the three principal lattice vectors. So in this case, A, B, and C are our principal lattice vectors. X, Y, and Z are the fractional coordinates. So how much of lattice vector A, how much of lattice vector B, how much of lattice vector C do we need to add together to get the position of this particular atom? So in this particular study, they looked at the positions of silicon and of oxygen at some different pressures. And they're describing those positions by fractional coordinates. Here, silicon, you only need one coordinate to describe it. Oxygen, you need all three. But we see that these positions change a little bit as we increase the pressure. So let's try some examples here. I'm going to start off with a very general lattice. This is a triclinic lattice. And again, I've defined principal lattice vectors A, B, and C. So first, let's say I want to draw a point in this cell. So I've given you the length of A, B, and C. But I'm also giving you, in this example, the fractional position of this point. So usually this would just be written 1/2, 1/4, 1/3, or sometimes it's written separated out. X equals 1/2, Y equals 1/4, Z equals 1/3. Now remember, what this means is you have some vector, and this vector describes the position of the atom, or whatever we're situating in the lattice, in terms of the three principal vectors. So we are going to look at 1/2 of A, 1/4 of B, and 1/3 of C, and this is going to describe the location of this position within the lattice. So that position is sitting right about here. Okay. As another example, maybe we have some point, we know where this is sitting in the lattice, and we'd like to give the fractional coordinates of this position. So for this particular example, and it's a little difficult to tell in this case, so why don't we make it a little easier, and why don't we say we know the position in Cartesian coordinates, so in XYZ space. In this case, I know the position of the atom, and I know the magnitude of the different lattice vectors. So to get the fractional coordinates, I need to divide these lengths by the lengths of the original vectors. So in the x direction, it's 1.15 angstroms, and we know the lattice vector A is aligned in the x direction, and it has a length of 4.6. So 1.15 over 4.6 equals 1/4. We can do the same thing for y, 4.4 over 8.8, which is the length of the B lattice vector, and this equals 1/2. And finally, for Z, we have 2.7 angstroms over 5.4 angstroms, and this also equals 1/2. So the position of this particular atom would be 1/4, 1/2, 1/2. Conventionally not written with commas, and certainly with no brackets or parentheses, as these have other significance, as you'll see shortly. Couple things to observe here. These are conventionally fractional, so they're between 0 and 1. And that is because, remember, this lattice is repeating. So if I gave a number of, say, 1 1/4, that's sitting somewhere in the neighboring unit cell, and I could bring that back to the original unit cell just by subtracting 1. And so 1 1/4 is identical to 1/4. So that's why they're usually given in terms of fractions or decimals between 0 and 1. Okay, let's try one more example. And in this case, I'm just situating the atom on a clearly defined position in the unit cell. So it's all the way on the front top face and about halfway down left to right. So I would say that the magnitude of the direction of this atom in the A direction is 1. The magnitude of the direction in B is about 1/2. Let's erase that, that's confusing. And the direction in C is, again, 1c. So this is 1 times the vector c. And so again, the position of this particular atom is going to be 1, 1/2, 1.